I'm Miss Metacentre and I'm a naval architect. Now you might be sitting there thinking, what on earth is a naval architect? Because a lot of people have never heard of that. A naval architect is a designer of ships and boats. And what that means is that we have some pretty specialist knowledge about something which is important to everybody, and that's the question of how things float and how they don't. That's very much our specialist subject, and it's a subject which a lot of people are very curious about. I get a lot of questions about it. A lot of people really want to understand how it works. How does a gigantic ship stay on top of the water? Stability is another one. I'm not going into that in this video, but the whole question of how do these huge cruise ships with their great tall superstructures stay upright? People really want to know the answers to this kind of thing. And yet I feel like it's an answer that doesn't often get given. A lot of people are going through the world with very little sort of real understanding of how floating works. And yet it's something that is crucial to us. Our lives depend on it every time we step on board a ship, a boat, a pontoon, a barge, anything like that, a floating pier arrangement, a houseboat. You're depending on that staying afloat. And yet most people never really get a good grasp on why it does float. And I think it's just a fascinating subject. I think it's really, really interesting how it works. It's one of these really neat little pieces of physics which informs our whole lives and makes things work that we could not exist in the earth without. And the theory of how this works was figured out by a guy called Archimedes a very, very long time ago. More than 2,000 years ago, Archimedes basically cracked this. And all our science to do with floating and sinking has been based on Archimedes' thinking ever since then. And I would say this is a really, really good subject to get a good grasp on. Partly because it'll satisfy your curiosity and you'll be able to satisfy the curiosity of other people, because as I say, it's a subject people really want to know about. And also, if you want to do any calculations which have anything to do with floating, sinking, ship safety, ship stability in the future, if you try and do it without first of all having a really good understanding of how floating works, you're going to have an incredibly hard time. The subject will be really, really dense and really, really opaque to you, really, really difficult to get through. But if you start off by understanding what it was that Archimedes understood over 2,000 years ago, suddenly that becomes much, much easier. So let's start from a very basic question. We have two objects here. Superficially, they look exactly the same. And we'll just see what happens when I put them in the water here. So, same objects apparently. Let them go. One floats, one sinks. And the first step to solving any sort of scientific problem is to try and imagine, why might it be that one of these objects has floated and the other one has sunk? And you can try and work out a hypothesis as to why that is, and then you can test that. So, a hypothesis a lot of people would come up with is they'd say, okay, one of them's heavier, because heavy things sink and light things float. And that is actually a really basic piece of intuitive understanding that we all have from our early childhood, that heavy objects sink and light objects float. So let's have a look and see if this is in fact true. These objects look exactly the same as each other, but there's only one way to know for sure whether our hypothesis is correct. So we've got a scale here. I'll try and get it sat neatly. There we are. And I'm going to weigh these objects. So first of all, the one that floated, 350 grams. Okay, so remember that. If you're not a metric person, that's somewhere in the order of, what would it be, about 12 ounces or so, roughly. Actually, I can tell you exactly. Let's, for the sake of the imperial people, 12.5 ounces. Not bad, eh? Okay, and the object that sank, 500 grams. So that one is 1 pound and 2 ounces roundabout. So we've got 500 grams and 350 grams. So our hypothesis is holding so far. The heavier object sank and the lighter object floated. What though if I had another object, completely different object, doesn't look similar to the other ones at all. Let's have a look. How heavy is this one? 500 grams. So let's have a look at what this does when it goes in the water, because it is the same weight as our sinking object. So now we're going to test two objects against each other, both of which weigh 500 grams. Now that's a bit of a puzzle, isn't it? Same weight, and our hypothesis was that heavier things sink and lighter things float. But these two objects are the same weight, and yet one of them is floating and the other one is not. So that means in the face of this additional evidence, we're going to have to revisit our hypothesis, because clearly it's not quite there, is it? And we're going to have to think, what is it that makes a difference between these two objects? They're different colours. I mean, science can surprise you, so you shouldn't dismiss anything at this stage. But you want to come up with a hypothesis which seems most plausible, and colour doesn't seem terribly likely at this point. They're just generally different looking. They are the same overall shape. One of them is larger and the other one is smaller, despite the fact they're the same weight. This one's bigger. So maybe we could start saying, okay, so it's something to do with weight and size. A heavier object will sink, but maybe if, as well as being heavier, it's also larger, it might not sink. Well, it's difficult to sort of come up with a really rock solid, a really watertight hypothesis from that, isn't it? So let's have a bit of a think about what's happening when we put these objects in the water. Put the object in the water, and I think we would all accept it's a fair principle that we don't have to prove at this point, that two things cannot be in the same place at the same time. If you take these two objects and you try to make them occupy the same space as each other, you're going to have no luck. If you want to put something in a particular position and there's something else there, you're going to have to remove the object that was originally there in order to put a new object in that place. There's only room for one thing in any given space at any given time. So what that means is this space isn't empty. Don't be deceived in thinking this is empty space. That is actually the thing which I think mostly causes people trouble in understanding floating, is that they think of the water as being empty space. It's not empty space. Water is heavy. It's there. It is an object which is taking up that space. You can lift it up. You can move it. What that means is you can't put this object into the water while the water's there. Water has to move out of the way. And let's just have a look at what's actually going on when you put an object in the water, but we'll do it in a smaller container, because in a big container like this, you can't really see what the water is doing. It's just a big mass. So let's have a look in a smaller container. Get our desk up here again. Welcome to my garage, by the way. I wouldn't say it's a good studio, but it's good enough. Alright, so what we've got here is we've got a measuring jug. And this measuring jug is filled with water up to 1.5 litres, 1,500 millilitres. So it's got a bit of headspace there. It's got a bit of headspace there, just about 500 millilitres of headspace. Slightly over, it's got the 1,000 millilitre mark just below the rim there. So let's try our various objects. Let's first of all try our first floating object, the 350 gram one. Put that in. And the water is moving away in order to allow the object space to sit in the container. Because remember, the water is not empty space. The water has to have space for itself. Water, as a matter of fact, is what's called incompressible. That means you cannot squash it. It occupies a certain amount of space, and that is the amount of space it occupies. If you want something else to be there, the water is going to move somewhere else. And as we put it in, the amount of water that has moved aside to let that object sit in there, we can read it off on this scale. So the amount of water apparently in the jug, although now it's water plus jam jar, it's moved up from 1,500, 1,850, so it's moved up by, near enough, 350 millilitres. Does that number sound familiar? It's a 350 gram object and the water has moved up by 350 millimetres. Not a coincidence. Alright, so we take that back out and you see the water returns to where it was before. There is a fixed amount of water in this And as I say, water's incompressible. It's not going to change how much of it there is. It's only going to move around. Let's try our sinking object then. So we put this in. This was a 500 gram object, the first of the two. Put it in. And again, our water's gone back to 1,500 because that's how much water is in there. Drop this in. The water moves out of its way. It sinks. And the water level has now gone up to 2,000 millilitres. So it's gone from 1,500 to 2,000. The water has risen up by 500 millilitres. Again, familiar number? It's a 500 gram object. The water's gone up by 500 millilitres again. Not an accident. Let's have a look at our second floating object. So this one's 500 grams. This one's 500 grams, but it's bigger, different size. Let's pop it in, see what it does. There's a bit of a bubble that needs to come out the bottom of this one. It's floating, but check it out. The water level has gone up to 2,000 again. So these two objects that were both 500 grams, they both pushed the water level up by 500 millilitres. And what's going on here is all to do with that water moving out the way. And the whole business of how things float is all to do with that water moving out of the way. What we generally say is we say the water is displaced, and that just means it was in a place and it's now in another place. We have displaced it. And whenever you put an object into water, you displace a certain amount of water. It has to move somewhere else. And the amount of water you displace dictates how much the water pushes back to get back into the place it was displaced from. So the water, you can totally anthropomorphize this. People don't like it. Some people don't like it. Physicists generally don't like it when you talk as if objects like water had personality. I am fine with that. The water doesn't like being pushed to one side and it's trying to get back to its place that it was in originally. It's essentially, that's a simple way of explaining it, but basically that is what's happening. The water is exerting a pressure, it's all about water pressure, on the object that is in it. And that pressure adds up to a force pushing the object back up. And that force pushing the object back up is the weight of the water that you pushed out the way. Alright, so in terms of the sinking object, that's a fairly simple sort of proposition to get your head around. You say, alright, so this object, we dump it in, and it sinks. And this object is just about exactly the right size to displace the same amount of water as it has in it. Now, it would be possible to have made that object even heavier. And if that object was even heavier, then it would weigh more than the water it displaced and it would still sink. Because you only get enough force up, you only get as much force up on it as the weight of the water that's pushed aside. This object has pushed aside exactly 500 millilitres of water. That gives it just about 500 grams of force up on it, but it weighs 500 grams, so it's not enough to make it float. It just sits there on the bottom. And you can't do this, obviously, but if I move it, it feels like it's almost weightless in there, because the weight that it has, its 500 gram weight, and the 500 gram weight of water pushing up on it is just about dead equal. It is just barely balanced to sink. If it was just fractionally lighter, it would slowly float up to the surface. But it doesn't. It's just not got enough oomph from that displaced water to get it to float. On the other hand, let's have a look at one of our floating objects. It weighs 350 grams and it has displaced 350 millilitres of water. If I were to push it in and try and make it sink, it would displace more, and that means that, so let's say I'll push it in until it has displaced 400 millilitres of water. So until I get to 400 grams of water pushing up on it, and it's only got 350 grams of weight pushing down, so if I let it go, up it pops. This is how it works. It's all about the weight of water you displace, and the same happens with the third object. Now that force, this one's got, as I said, a bit of a bubble that needs to escape from the bottom. There we are. And this one again weighs 500 grams, has easily got 500 grams of water weight pushing up on it. So if I push that in, It just displaces the water more, the weight acting up on it increases. Now I'm talking about the weight acting up on it. Weights don't act up. Don't be so silly. We call that buoyancy, and you will have heard that phrase because, or that word, that's a word that people are generally familiar with, even when they're a bit hazy on what it means. And buoyancy just means the force that acts up on something that's sitting in a fluid. It isn't unique to water. All sorts of fluids have buoyancy. Any liquid has it. Even gases have it. This is how helium balloons float, because the air has a buoyancy force that acts on it. And the helium balloon is so light and so big that that force is sufficient to push it up. So buoyancy is not unique to water, it happens in any fluid. And buoyancy just is that force acting up on an object immersed in water, which is equal to the weight of the water that it displaces. And how much water you have, how much buoyancy you have, depends how much water you displace, and therefore it depends how big your object is. The bigger it is, the more water it's capable of displacing. And if it has quite a lot of extra volume sticking up above the water, that means it has the capability to displace a whole lot more water. So even if it gets pushed down, it's going to bob back up again. So things that people misunderstand about buoyancy. The other thing is that people tend to think buoyancy only acts on light objects. Well, that's not true. You saw when I put the sinking object in. Now, although it's sinking and it's sitting on the bottom, it feels almost weightless. It's still got the buoyancy acting on it. It's just not big enough to push it up to the surface, but still makes it feel light. That's why when you're in a swimming pool, you feel lovely and light, and even the parts of you that are under the water, like your legs, they still feel lightweight because the buoyancy is acting up on everything, absolutely everything. So wherever you're sitting right now, unless you are an astronaut on a spacewalk in the vacuum of space, if you're sitting surrounded by air, you have a buoyancy force on you. Now, air's doesn't produce much of a buoyancy force, so it's very small compared to your weight, but it is there. All right, so in order to work out how much buoyancy an object has, you need to know its displacement, how much water it displaces. What does that displacement depend on? Well, it depends on the size of the object under the water. This part that's sitting above the water, that's useful for spare buoyancy if something bad happens. But it's not actually giving you buoyancy at this moment in time. The only thing that's giving you buoyancy is the bit of the object that's underwater. So the whole business of naval architecture and working out a ship's flotation, a ship's stability, is all about the shape of that underwater part. And if you worked out the shape of that, you could weigh that object. So we know how heavy it is because we put it on the scale. We also know how heavy it is because we put it in the water. So we put it in the water and we see, oh, it displaces 500 millilitres of water, therefore it weighs 500 grams because 1 milliliter of water weighs a gram if it's fresh water. I should have told you that. That's one of the sort of nice constants with our measurement system if we're using the metric system, is that 1 milliliter of water weighs a gram. Fresh water, not salt. Salt water is a bit heavier. All right, so that means you can weigh it either by the scale or by the displacement. And you can do this. You can weigh this. This weighing trick only works for a floating object because, as I said, this sinking object's displacing exactly its weight, but it could just as well be even heavier than that, in which case it would be displacing less than its weight, so you wouldn't be able to weigh it that way. But you can weigh a floating object. And the other way you can weigh it is, you can see this is a nice, neat cylindrical shape. So if you measured the radius of this shape and you measured its height, you could go, okay, well, the circle is pi r squared, and then multiply it by the height, not the overall height of the object. Remember, this part is only spare buoyancy. It's not giving us buoyancy right now. The height from the bottom to the surface of the water, just the underwater part. And if you worked out that volume, and then you said, okay, well, it's fresh water, so 1 milliliter weighs 1 gram, you could work out that it weighs 500 grams. And if you made that object heavier, it would float deeper, and so your calculation would give you a greater weight. This is how you weigh ships. So let's have a look. Ships, as a rule, are too large to fit on scales. Some small boats can be weighed on a crane or a hoist, something like that, but most, whoops, dropped the table in the water. Most large vessels are much, much too big to ever go on a scale. Even weighing lorries is quite a performance. There are scales big enough, weigh bridges big enough for them. But ships, they just aren't. So how do you weigh a ship? And this is really necessary for its safety. You need to know how heavy it is at all times. Well, you calculate how much of it is under the water. So here we have a ship. This ship is a fairly simple shape. Just basic. So the maths on working out the volume of this would be fairly simple. If you could work out the area of that shape there, which you could just do by using a bit of graph paper and counting up the squares. And then you work out how much height of it, how much depth of it is in the water. This is called the draught. Then you can calculate how much ship is under the water and work out the weight of the ship from that. So put that ship in the water. It's floating at a draught, and this is an important piece of vocabulary. So the depth of the ship is right the way up to the deck, but the draught is just how much of it's in the water. Don't get those two mixed up. So it is sitting at a draught of about 1 3/4 centimetres. It's got draught marks marked on the side here. A little bit closer so that you can see. And those draught marks are marked in centimetres. So it's got a draught of about 1 3/4 centimetres. So if you worked out the area of this and you multiplied it by that draught, that would give you a volume of the underwater part of this ship. And that volume is called the volume displacement. And all that means is the volume of water you displaced. You displaced so many cubic centimetres. This is a wee ship. Full-size ships you would measure in cubic metres. And then you use that volume displacement to work out how much weight of water is displaced, or mass. Now, I'm not going to get into weight versus mass, but it is an important distinction, really. That weight is actually the force due to gravity, and mass is actually the amount of stuff that is contained in the object. So mass is what we measure when we're talking about grams and kilograms, really, not weight. Weight's measured in newtons. But if we take that volume displacement and we multiply it by the density of the water, now the density of fresh water is 1 tonne per cubic metre. So that's why you get that nice millimetres to grams conversion. If it's salt water, you really have to be getting into a bit more into the density, because it matters, it changes what depth it floats at and so forth. But you could weigh that, and that is how you weigh any size of ship. Now, obviously, most ships are not this shape. Most ships are not just a basic boat shape and then a vertical. They have a more complex shape. But there are various secret methods that naval architects can use to work out the volume of shapes like that. So all that we do is we would go and we would measure the draught on the ship if we wanted to know how heavy it was. And then we would use that to say, okay, well, how much of that shape is under the water? What volume is that? Work that out in cubic metres. That's its volume displacement. And then you would use the density to work out how many tonnes of water that is. Now, the how many tonnes of water, that's your mass displacement. And this is really important. If you're just watching this video just for curiosity, you won't really care about the sort of the vagaries of the word displacement. It doesn't matter to you. But if you're dealing with like physics and engineering, the word displacement is a bit of a problem. It's used different ways in all sorts of different fields. It's often used to mean like how far a thing has moved. That is not how it's used in naval architecture. It's always used to mean how heavy is my ship in tonnes. That's its displacement. Because you're saying, my ship has a displacement of 500 tonnes. It displaces 500 tonnes of water when it's floating. That means it weighs 500 tonnes, because those two numbers are always equal for a floating object. If it sinks, all bets are off. But if it's floating, it's always equal. Alright, so I've got two ships here. And this one is a similarly, it's got some sand in it. It's a similarly simple shape, and it's also got little draft marks on it. This is a little cute one. And again, you can take the same method to work out how heavy that ship is. And the last thing I'm going to show you is a little bit about how how much weight is on board the ship affects how deep it will sit in the water, what its draft is. Because this is something which I think people really sometimes struggle to get their head around. I say the displacement is the weight of the ship, and it's determined by how deep it's sitting in the water, its draft. But then what happens if you put a weight on it? Well, it sits deeper in the water, and because it's sitting deeper in the water, it is still, the mass of water it displaces still matches its own mass. It's still the same amount, and that rule will never be broken. So let's see what happens if we load the big one up. I'll take the little one out of the way for the moment. So I've got here a payload, a dead weight is what you call it in shipping terms, of tuna. So this is a tuna carrier. And I'm going to say, so I said it was about 1 3/4 centimetres draft. So I'm going to put a can of tuna in the bow. And I don't know if you noticed that made the bow go down a little bit. Ships are seesaws basically. And this is something which, if you get interested in ship flotation, stability, all that kind of thing, this becomes a really important principle. But it is never really more complicated than the ship is a seesaw. You put a weight on one end, that end goes down. You put a weight on the other end, that end goes down. And when it becomes more complicated is when you discover you didn't understand seesaws quite as well as you did. But that's a kind of that's a kind of forthcoming attraction. I'm not going to be talking about seesaw ships today, but I'll put another tuna can in the stern so that it's floating level. It's not quite level. Pull that, push that one forward. Okay, and it is now sitting at just about 2.5 centimetres draft. So you see, as you added more weight, it had to displace more water because it needed more buoyancy to support it. Where does it get that buoyancy from? It has to displace the water to get it. So it has to sink down to get it, and you get that, still get that beautiful balance where the mass of water displaced is equal to the mass of the ship and all of the stuff that is on it. In this case, it's tuna fish cargo. Let's see if we can put it down a little bit further. See if we can get it to go down a full centimetre. Let's see. So it's about just over 2.5 just now. Not quite. Yeah, I would say that's it. So it's now sunk a full centimetre. And that is a really important sort of feature of this ship, is how much weight do you put on it to make it sink by a centimetre. Obviously calculating the sort of the underwater shape of a ship is a complicated business if it's not a simple shape like this one. And so you need a lot of shortcuts and rules of thumb. And one of the shortcuts that is used a lot on board ship is how much weight do you need to put on this ship to make it sink by a centimetre? And that's just used to do quick and dirty calculations for cargo loading. This is obviously a very small ship, and I'm sure you can imagine that the larger your ship, the more weight you will be able to put on it before it sinks by a centimetre. And that figure is called the tonnes per centimetre immersion for that ship. So let's see, what is the tonnes per centimetre for this ship? I'm going to put the desk back up so that I can put the scale on it. The ship is still down there, don't worry, it hasn't sunk. Alright, so this will not be tonnes per centimetre, this will be grams per centimetre. 1 tuna can, 2 tuna cans, and 2 little spiders. 422 grams per centimetre. So you could work out from that if you put 844 grams on this, it would sink by 2 centimetres. If you put 211 grams on it, it would sink by 0.5 centimetre. And that is, it's obviously, if your shape of your ship is very curved, it might not be super accurate, but for small differences in weight, it is very accurate. So let's do it for the other ship. And then we will finish this little demo up. So our second ship, our little cute one, take the big one out of the way. Pardon the state of these ships, they are coming well overdue for dry docking and service. Okay, so this little ship is floating pretty much bang on 2 centimetre draft. It's the actual, it's got water in it. If you know anything about the Herald of Free Enterprise, you know that's a bad thing. If you don't know anything about it, go Google it. Yeah, so it wasn't much water, 2 centimetres, enough to destabilise it though. Right, okay, so we want to see how much weight will make this one go down to 3 centimetres, increase the draft by a centimetre. So pop these in. Nope. I need to keep them nice and balanced. I do have draft marks on both sides. I need to keep them nice and balanced. That's about 2.5. Getting there. Is that there? Yes, there we are. Okay, it can be difficult when the water's very clear to see exactly where it's falling on the hull. Okay, so find out what our grams per centimetre immersion of this little ship is. As I say, for full-size ships it would always be tons per centimetre. Because ships are big. I don't know if you've noticed that. Even most boats are quite big. .149 grams per centimetre. So nearly 150, just shy of it. And you notice how much smaller that is. Much, much smaller grams per centimetre immersion on this little ship than it is on the big one. Why? Purely a question of size and specifically area. So these ships are really simple shape. The area of the flat bottom is the same area that it has all the way up. Obviously a full-size ship wouldn't be like that. It would be a little bit more complicated. But this area here, the point is the area where it sits in the water, is larger on this ship. And just as with any, you know, the larger the area of the wheelbase on your truck, the more space, the more weight you're going to be able to carry with it. The larger your feet, the more weight you're able to carry when you're walking. It's just much the same. This is the base of support of the ship where it sits in the water. The larger it is, the more weight it can carry with less sinking. Okay, so that's a bit of a quick intro with some demonstrations of flotation, how it works, and a little bit of Archimedes, a little bit of sort of going through the basics of how that actually functions. And I'll just finish off by basically settling another myth that people have, or a misunderstanding that people have about buoyancy. And that is that people think that buoyancy is the opposite of gravity. It's not. Buoyancy is caused by gravity. If you don't have gravity, you don't have buoyancy. So if you tried to swim in a swimming pool in space, you would never be able to float. You would still be able to swim, but you wouldn't be able to float because there would be no gravity. And the reason for that is that what ultimately causes buoyancy is the fact that the water is being pulled down by gravity, and that means that the deeper you go in the water, the greater the pressure is on you. And that is that difference in pressure as you go down which causes buoyancy in the first place. So no gravity, no buoyancy. All right, back with more demonstrations in the future, no doubt. Goodbye.